We are given the following problem. An 800 Newton passenger in a car, sorry, this should say car, presses against the car door with a 200 Newton force when the car makes a left turn at 13 meters a second. The faulty door will pop open under a force of 800 newtons. Of the following, the least speed for which the man is thrown out of the car is 14 meters a second, 19 meters a second, 20 meters a second, 26 meters a second, or 52 meters a second. So the first thing that we want to look at is what type of motions we're dealing with here, and try to come up with some sort of free body diagram to kind of figure out what laws will be needed to solve this problem. So we know that it's traveling in a certain direction, and it says that it makes a left turn. So it's going to go left. But we know that cars aren't just going to suddenly veer off in a direction like that. They're going to follow some sort of curved path as they turn. So this would be indicative of a left turn. So this tells us that we are probably dealing with some type of circular motion. So continuing with this, we know that a car is going through a turn. It's going to follow this general motion as it goes through the curve because it doesn't just instantaneously go from this direction to suddenly that direction. So if we were to kind of zoom in, you can kind of think of this as what's happening there. So we're going to go ahead and just draw a circle here to simplify things, and we're going to only be looking at essentially this section. So let's see. The car makes a left turn at 13 meters a second. So we're going to assume that it's maintaining a speed of 13 meters a second. And we know, so this is the velocity. Let's use blue. So its velocity is 13 meters a second in this direction. And as it progresses through the turn, 13 meters a second, we're going to hold our speed the same, but the direction is changing. And so we know that in order for there to be a change in our direction, there has to be some sort of external force acting on it. So in this case, we have its speed remains constant, but its direction is changing. And if we look at the differences between these, so imagine that we are, translating these vectors. You are going to get a small. Let's back up here for a minute. Let's do this. Let's translate these vectors. So we're going to do these in green. So that's the first vector. Here's the... Now remember, the magnitude here is the same. So here's the second vector. Wait, let me change that just slightly. It's hard to translate these without actually dragging them. And so these represent the small changes in, let's make this, it's supposed to be more like this. And the reason why I'm being very particular about that is because if you then translate these back here, you will see that we have a center-seeking force. And if we continued that, velocity is always tangent to as it was banking around the curve till eventually we end up here. but in order for it to keep changing direction, there has to be that external force. And so what that force would be is the friction between the tires of the car and the road itself. Because if we were to actually remove the friction, I actually experienced this myself. If you're trying to maintain a certain speed, like let's say you're going 13 meters a second around a turn, if you were to, say, drive over some ice or something, it would not be able to, it would slide out of that turn. And so that's just some of the conceptual. So now let's actually look at the calculations here. So it says in the problem, so we know we're doing with uniform circular motion, so this centripetal force, let's just get our formula down here first. So that's going to be m d squared over r. There. Now we can start working with what we got. So we are given that it is 200 newtons of force experienced by the person against the door. And so we don't know the mass. No, we do know the mass. And we know the velocity. And let's go ahead and find out his mass really quick. Now remember, 800 newtons is a measure of force, which is weight in this case. So if we take that 800 newtons and divide it by the gravity constant, we should get 81.6327 kilograms. That might not be approximate. That might be, let's see, let's verify. No, that's exact, it looks like. Okay. So we're going to use that as our value there, and we are going to be solving for r. So we are going to have 81.6327. Just get these computations out of the way really quick. So what we're trying to do is we are trying to solve for this r, which can be thought of as like the center to which the friction force is seeking as we are going through the turn. Okay, so where was I? So we've got 13. And then once we solve for this, what we can do is, here, let me just jump ahead real quick here and get these computations out of the way. 7 times. Okay, so our R is representative in meters of our distance from the center of where the friction is seeking. This is in meters. So it says that the faulty door will open under a force of 800 newtons. So what we want to do is figure out for what value of velocity we will experience 800 newtons of force to pop the door open so that the person will fly out of the car. Very unfortunate, but that's what we're checking. So we're going to plug in this value here. Times 81. Oh wait, yep, and then we wanted to solve for the velocity that will cause that. So what we'll end up with is let's go ahead and throw that in, and we are going to get exactly 26 meters a second. So our answer was in our choices here. We have 26 meters a second. Alrighty, so we're going to do something a little bit different for this portion. I unfortunately lost the audio, and this happened to be my favorite, in particular among the problems that we have done.
So I'll do my best to just kind of summarize what I was talking about. Unfortunately, I'm not going to go into as great of detail as I initially did. So yeah, without further ado, let's get through this section. Okay, so right around here, I'm just reading what the prompt is, and as you can just read it for yourself there. Pause the video if you need to. And what I'm doing here is I'm first giving the definition of momentum as mass times velocity, because of it relates to impulse a little bit later on. So then here I give I relate force to momentum. So we're saying that force is mass times acceleration, and we know that acceleration is the derivative of velocity with respect to time. And I was probably thinking slow when I did this. Okay, so what do I do? I think I'm setting force equal to dp dt. Yeah, because mass, even if we move that into the differential operator, it won't be affected by it. Yeah, there we go. So force, we related force to momentum. It looks like I paused here. Oh no, the video's still going. I thought it was going to run out. So yeah, we relate that. There shouldn't be much left in this clip. We're going to go ahead and we're going to jump over to the next portion, which is right here. Let's go ahead and throw this down. I know this is kind of a weird way of looking at how I do things. You're getting a little behind the scenes here. Okay. So then it looks like I create some formal statements. We let P be the change in can't even speak. P is change in momentum, and Q is going to be net external force, I think. Yeah. So there is a change in momentum if and only if there is a net external force. I think that's what I'm setting up here. Yep. This is definitely an if and only if. Okay, and then let's see. I say Q, therefore P. We because we are given the force, so we know that there is a change in momentum. And then so we've related momentum to force. I swear this is going somewhere. Where oh boy. So I'm just doing a bunch of talking here. It looks like I'm going to give the definition of impulse now. Impulse being change in momentum, where change in momentum is momentum final minus momentum initial. Let's see if I do that. Oh no, okay, so I'm using net impulse over a time interval. dp dt, so it's just dp, which would be momentum. Yeah, this would be a momentum final minus momentum initial. At some points, I'll sidetrack and look at it where instead of putting dp dt here, we just have f dt. And I show that despite whatever perspective you take, they're going to come out computationally the same. Yeah, momentum final minus momentum initial. Yeah. And then there we go. We're relating net impulse to as a change in impulse, which is... Oh, I can't scroll back down. While the video is playing. So I'm just talking. I'm so sorry that I lost the audio. And then... Yeah, let's fast forward here a little bit. Okay. Yeah, here we go. So now I'm looking at it through this perspective. So you just integrate the force function that we're given. So the momentum final minus the momentum initial that you jump straight to is good if you don't know the force function. Like, let's say you just know the mass of the object you're working with and its velocities. You can use that. It just depends on what your given knowns are. Don't have the force function, you can just say momentum final minus momentum initial. If you have a force function, you can just do this integration. Let's jump ahead. No, where is it? Here we go. So then I throw that into a calculator. We get 4.62 kilogram meters a second. What am I doing there? I don't remember. What was I saying? Mass times. Okay, so I was showing that the answer we arrived at is the correct choice, and it's in one of our multiple choices. Oh, that's what I was doing there. I think I was looking at units, kilogram meters a second. Okay. Anyways, right. So we didn't actually. That's what happened. I stopped at this point from this perspective, and I said, let's just do this because we have the force function. I ran over there. Now I was saying we have the initial momentum being 0, and then I was saying what's the final momentum. So to find the final momentum, we know that momentum is equal to mass times velocity, but we are not given velocity. We are given accelerations. Wait, let me think. Hold on, it's going to be in the next clip. Okay, so in the next one, what did we do? Let's pop this bad boy up. So, yeah, we were...
Speed for which the man is thrown out of the car is...
Whoops, what happened? Oh, okay. Yeah, the videos are merging as I drag them. That kind of stinks. Okay, so where were we? I jump back over to this. FDT is dp. We integrate. Oh yeah, we're finding momentum function. So I can get the upper bound on the integral there. But why did I do that? I did that because FDT is dp/dt. Yeah, I was trying to find the momentum because P is equal to mv. Okay, that's why I integrated it. Okay, so then yeah, I showed that you come out to the same values here, right? Wait, let's back up a little bit because I didn't narrate this. Okay, yeah, so right here, this was the momentum. That's, you plug in 2 seconds to get the momentum final. So that's the upper bound on the integral. That's how we get that there. And then, yeah, this one was very computation focused, but I tried to make sure that the focus wasn't just on running the computations, but relating force to momentum and then working your way up towards impulse. Yep, so that was the gist of what this was.
In this next problem, we are given that an object at the surface of Earth at a distance of r from the center of the Earth weighs 90 newtons. Its weight at a distance of 3r from the center of the Earth is... And then we're given a bunch of different choices. So there's a really quick way that we can do this, and then there's kind of the long way to do it. And so we're going to look at two things here first. The first thing we're going to look at is that Newton's law of gravitation has an inverse proportionality relationship between, or with the distance of the bodies squared. So what that means is if we experience 90 newtons at a distance of r, then at a distance of 3r, if we were to do 3 squared, and just to be clear that here's the inverse, right? So 90 divided by the 1 would just be 90, and then if we're looking at 3r, we'll just plug in those. You would get 1/9, and 1/9 of 90 newtons is 10 newtons. So that's the really quick and dirty way of doing it. So if we want to like look at, some hard numbers and a little diagram here of this, let's say that this is the Earth and the center of mass is there. This r distance is actually the radius of the Earth, and then we have a body here experiencing 90 newtons of gravitational force. We want to then know, hey, what is it experiencing at 3r? So if that is 1.2 to 3.2, So it's going to be somewhere else, right? 1, 2, 3. Somewhere around there. Okay. Sorry, I want to make sure I got the measurements. So then what would a body that's somewhere out here experience in newtons? We can use the formula with the gravitational constant, m1, m2, and the distance between the bodies. Let's use lowercase r squared. Okay, so we can start with what we know and plug in some other known constants. We know that the gravity constant is 6.67, and the mass of the first body, let's call this m1, and then the Earth m2. What we can do is first find m1, which is 90 divided by 9.8 meters a second, or 90 divided by 9.8. We're going to get 9.18367. And m2, this is the mass of the Earth. It's going to be 5.972 times. Oh, we're just going to use the E notation, E24. Cool, we've got that. Sorry, I mislabeled that. That's M2. And the radius of the Earth, I gotta double check this. It should be... What is the radius of the Earth? Oh no, that's what we can actually solve for that. We have M1, we have M2, we have gravity, we have force. Yeah, we don't even need to look that up. We can just verify that. Okay, so if we rearrange this equation and plug in our knowns, we should be taking r is equal to the square root of... Here, let's not try to do too much of this in our head. We've got 6.67 e negative 11. We'll just put m1, m2 here for now. And this was divided by r squared, which means we flipped those. He's on the bottom. Yeah, okay, so that's divided by 90 here. Times... I'm not going to bother writing these out. Just assume that these are plugged in here. I'm not going to physically write them. We're going to throw that into a calculator and see what we get for the value of r. We're going to get 6.67 e negative 11. Make sure I plug these in right. Oops, something's wrong with the syntax there. And that checks out from what I looked online. That matches the radius. What I was a little concerned about is what we would get when we plug them back in. If I plug this value for the r back in here, which was the only missing, this was the only unknown in the equation, what we would have gotten is 90.0301. It's very close to 90 newtons. And so we found our r, and I was just trying to verify that this r, when you plug it back in, would get very close to the original 90 that we saw. And it does. And so if we were to then triple this radius of the Earth and plug it back into the formula, we should get very close to 10 newtons as well. And see, this is why, you know, when you're just using the formula versus using concepts like this, especially when you're crunched for time, this is a much better approach to doing it, where we know that there's an inverse square law or relationship, because then you can just do this and you can quickly arrive at 10 newtons. So let's just see what that number spits out when we use the values we've done through computations. We're going to get 6.3743536. I'm just plugging these in. We are tripling the distance and plugging in the other knowns times Yeah, okay, so plugging in, so what I did was we had this. We wanted to know our new F. And so we plugged in our known G, we plugged in our known M1, we plugged in our known M2, and we took this value here and plugged it in times 3 and squared it. And after evaluating that, what we end up with is 10.0033 newtons. So very close to 10 newtons, which is what we expected here. Yeah, so here were the three problems that we had. We had the one with the car banking around a turn. We had the net impulse of a particle. And then we had Newton's law of gravitation.